when the user locks their collateral into the DAI stablecoin system and then mint DAI, this DAI will accrue interest. When the user repays the DAI to unlock their collateral, they'll have to pay this interest on the DAI that they borrowed. Inside the DAI stablecoin system, this interest is called a stability fee. Mint DAI and it accrues stability fee. The stability fee compounds every second. If you borrow DAI and then do not repay for a long time, then your debt will grow exponentially. Also, the stability fee rate may change at any second. So in theory, this stability fee rate can be different at every second. The algorithm that is used inside the DAI stablecoin system to calculate the stability fee for all users is not intuitive. To understand how this algorithm works, let's first take a step back and go through an example of what the debt will be when a user mints some amount of DAI, and over some time period, let's calculate how much debt this user will have to repay. So as an example, let's say that a user mints D amount of DAI at time K. And we want to find what is the debt. This will be the amount of DAI that they borrow, plus the stability fee after J seconds. As a reminder, the stability fee rate can change at any moment, so let's denote RT to be equal to the stability fee rate at time T. For example, on the right, let's say at time K, the stability fee rate is RK, and at K plus 1, it jumps to RK plus 1, and then at K plus 2, the stability fee rate jumps down to RK plus 2, and then so on. Now, let's plot how much debt the user owes to the DAI stablecoin system over time. At time K, this user borrowed D amount of DAI from the DAI stablecoin system. So the debt that they owe is D. At this moment, it has not accrued any stability fee. How about at K plus 1? 1 second after this user has borrowed DAI. Well, we can take a look at this graph, and from K to K plus 1, the stability fee rate is RK. And 1 second has elapsed, so the amount of DAI that this user will owe is D times 1 plus RK. For example, let's say that this RK is 5%. Rewriting this as decimal number, this will be 0.05. So this will be D times 1 plus 0.05. How about at K plus 2? Well, at K plus 1, the user owed D times 1 plus RK. So at time K plus 2, we need to apply interest to D times 1 plus RK. The interest rate between K plus 1 and K plus 2 is RK plus 1. So to this number, we need to multiply this by 1 plus RK plus 1. And then at K plus 3, it follows the same pattern. We start with the amount this user owed at time K plus 2, and to this number, we apply the interest. The interest between time K plus 2 and K plus 3 is RK plus 2, and 1 second has elapsed, so to this original amount, we multiply this by 1 plus RK plus 2. The pattern continues until K plus J. At K plus J, the amount that the user owes to the DAI stablecoin system is given by this formula. Multiply the original amount by all of the interest at each second. Up until the last second, K plus J minus 1. Okay, so this is the amount of debt that the user owes after J seconds. Now let's think for a second how we might implement this in a Solidity smart contract. At each second, we might have a different interest rate, and to calculate the debt, we need to somehow calculate this expression. One way we might be able to do this is to store the interest rate for each second, and then also store the timestamp when this user borrowed D amount of DAI. And then run a for loop to multiply D by 1 plus RK, and then multiply that by 1 plus RK plus 1, and so on all the way up to 1 plus RK plus J minus 1. The problem with this approach is that the longer the user borrows DAI, this computation will become more expensive. It takes more steps to calculate this amount of debt that the user owes. The way that the DAI stablecoin system solves this problem of calculating the debt for all users is by introducing what's called a rate accumulation function. This is defined to be the multiplication of all of the stability fee rates ever since this stability fee rate was initialized. More precisely, let's define capital RT to be equal to 1 plus R0, where R0 is a stability fee rate at time 0 when the stability fee rate was first initialized. And then after 1 second, we have 1 plus R1, and then after another second, we have 1 plus R2, and so on, all the way up to the current timestamp 1 plus RT. Let's see how this rate accumulation function solves the problem of how to quickly calculate the debt for all users. To see how this rate accumulation function works, let's write the det from example above using RT. As a reminder, the user borrowed D amount of DAI. And after j seconds, this D has accumulated this much amount of det. Okay, so let's rewrite this det using capital RT. This is equal to, we have the D, the amount of DAI that was borrowed. And then on the top, we can match this rate accumulation function by saying multiply D by all of the stability fee rates ever since the stability fee rate was initialized. R0, R1, R2, all the way up to the current timestamp RK plus J minus 1. Now, from this equation, to get back to this equation, we have some extra terms that we need to remove. For example, we have the 1 plus R0 that is present here, but not over here. And the same goes for 1 plus R1 that we have over here, but not over here. So we need to cancel out all of these terms. So let's divide this top multiplication by 1 plus R0 to cancel out the first term, 1 plus R1 to cancel out the second term, 1 plus R2 to cancel out the third term, and so on, all the way up to 1 plus RK minus 1. When we do this, all of the terms from R0 to RK minus 1 cancel out. And we're left with, on the top, the multiplication will start from 1 plus RK. And this is equal to, we still have the D. The top part, we can rewrite it using the rate accumulation function. This will be capital R of K plus J minus 1. And the bottom will be R of K minus 1. And this is the det that the user owes, rewritten using the rate accumulation function. Now at first glance, this doesn't look so useful. We just rewrote this equation in a different way. However, the benefit of rewriting this user's det using the rate accumulation function is that now we can calculate all users' det with two operations. Multiply their det by the current rate accumulation function and then divide by the rate accumulation function when they borrow this D amount of DAI. This is way more efficient than what we had before. Before, we had to multiply all of these rates to calculate the det that the user owes. However, now we can just keep track of a global rate accumulation function and then multiply by the current rate accumulation function and then divide by another rate accumulation function, which we can store when the user borrows this amount of DAI. And now we're ready to understand the algorithm that calculates det for all users in the DAI stablecoin system. Realistically, when a user borrows DAI, the amount of DAI that they borrow over time may change. For example, they might borrow 100 DAI today, and then a week later they might borrow an additional 100 DAI. Even in such cases, we'll see in this example that the algorithm is able to still calculate the correct amount of DAI plus the det that the user owes to the system. For example, let's say that at time k, the user mints D amount of DAI. Over time, this DAI will accrue stability fee. Let's denote the original amount plus the stability fee that the user has to repay as capital D. Let's also say that after j second, this user decided to borrow an additional delta D amount of DAI. So now the det that the user owes will be the D, which will be the original amount of DAI that they borrowed, lowercase d, plus the stability fee, which is all included in this capital D, plus the current amount that they borrow, delta D. And then over time, this amount, capital D plus delta D, will accrue stability fee. And now let's ask the question, what is the total debt that this user has to repay after n seconds from k? K is the time that this user borrowed lowercase d amount of DAI. We'll use the rate accumulation function to calculate the debt that this user will have to repay. And we'll break this problem into two parts. We'll calculate the debt that the user owes at k plus j, and then we'll recalculate the debt that the user owes at k plus n. Okay, let's begin. Let's first calculate the debt that the user owes at time k plus j before minting this delta D amount of DAI. Well, from the previous example, we saw that the debt that the user owes can be calculated by the rate accumulation function. Take the current rate accumulation function at time k plus j, and then divide by the rate accumulation function when the user minted D amount of DAI. How about after minting an additional delta D amount of DAI? What is the debt that the user owes to the MakerDAO stablecoin system? Well, at time k plus j, since no time has elapsed, this is the amount that the user has to repay. This part includes the stability fee rate on this lowercase d, and then the amount that they additionally borrowed at this second. Okay, so this is the amount that the user owes at time k plus j after minting delta D amount of DAI. How about at time k plus n? Well, to begin with, the user owed this much amount of debt at time k plus j after minting delta D. And from here, this is the principal amount that the user has to repay. From here, we'll need to apply the interest rate over every second until time k plus n. This is accomplished by multiplying this principal amount by the rate accumulation function. The current rate accumulation function at time k plus n is rk plus n minus 1. The rate accumulation function when this user borrowed this much amount of DAI is rk plus j minus 1. Next, let's unpack this equation. We multiply the inner terms by the outer term that involves rate accumulation functions. Take a look at the first term. We have rk plus j minus 1 over here, and we also have rk plus j minus 1 over here. And these two cancel out. Simplify it and we get these two terms. And finally, let's simplify these terms one more time. Notice that we have rk plus n minus 1, and we also have rk plus n minus 1. So we can factor out this term. After factoring out rk plus n minus 1, we get the equation in our final form. Now notice that this rate accumulation function, rk minus 1, will be the value of the rate accumulation function when the user borrowed the amount of DAI. And the value of rate accumulation function rk plus j minus 1 will be the value of this rate accumulation function when the user borrowed delta D amount of DAI. And all of these terms are multiplied by the current rate accumulation function rk plus n minus 1. This is the equation for the amount of debt that the user owes after n seconds, and also considering that over time the amount of DAI that they borrow may change. Most importantly, this equation also shows us how to implement our algorithm where we can use the rate accumulation function to calculate debt for all users, even when we consider the case where the amount of DAI that they borrow may change over time. What we can see from this equation is that whenever a user either borrows or repays some amount of DAI, we divide the amount of DAI that the user additionally borrowed or repaid by the value of the rate accumulation function when they either borrowed or repaid. Sum this all up and then store it in a mapping for each user. Multiply by the current rate accumulation function to calculate the current debt that the user owes to the MakerDAO stablecoin system. And this is how the MakerDAO stablecoin system is able to calculate debt for all users.